Good afternoon. My name is Mauricio Araya. I work for Total Energies here in Houston, R&D. This is a collaboration with the Stony Brook University. Most of the work was done by actually Bodhi. Bodhi is a PhD student, advised by Professor Barbara Chapman. So basically the idea here is that Barbara Chapman has been working, she's one of the leaders of OpenMP, working on it for a while. Bodhi was really interested to work on OpenMP target of loading, and push forward towards that direction. And like 2 years ago, Johannes Dorfert and people from Lawrence Livermore put out a paper where they do remote offloading. Basically, instead of just doing OpenMP offloading within the same node, you can offload work to a GPU on a different node. So now it's a distributed thing, right? So we were interested to see if, with Bodhi, if we could push this idea forward to really give it a good shot and see if we can, this is gonna hurt, but eliminate MPI from the picture, basically, and just have OpenMP as the parallel interface, right? I know from previous experiences that that will be impossible because the MPI mafia will kill us in the process, but we will give it a shot. But you can imagine that for hyperscalers, to have one thing less to think about it will be a thing. And Michael showed how that affects. MPI is a whole jungle in itself, right? Well, anyway, let's go into it. Yes, I have the legal thing. 1, 2, 3, gone. Okay, so why are we doing this? I sort of give you the gist of what we are doing this, then some implementation results of what we did, implementation of what we did, and then results, and then some conclusions and roadmap. So the why is basically here, very succinctly and cartoonish, but nowadays all systems are highly hierarchical. Maybe it's going to be worse in time, and for exascale system, yeah, you name it. So there's issues with the MPIX, whatever is your X. In particular, the perspective is OpenMP being the X here, but you have any kind of programming model at node level, shared memory level, this might be useful for you. So there's issues about programmability, complexity, maintainability, scalability, overheads, debugging, you name it with the MPI. Every time you run your benchmark, you have to try OpenMP, OpenMPI, Intel MPI, MPPitch, and so on, and try to figure out what Thomas was doing previously, which is what's the sweet spot, basically, with all these layers. So if you can simplify that, that's a good thing. That's kind of our idea, make this simple, but at the same time, easier to program, right? Parallel programming, you start with the serial code. First thing you try is shared memory. Most of the universities teach OpenMP at some point. I don't think people are learning pthreads anymore, but that will be the other way. But OpenMP standard is well known, has been implemented in most of compilers, right? So it's a good point to start with programmability, simple and consistent, then portability, because it's been ported to everything. Once you have your OpenMP code running, it will run everywhere. Different performance, of course, but that's a good thing. And try to keep performance as much as possible. There's always a trade-off. There's no free lunch, right? But we try to keep performance when we're playing with the programming models, right? So we go from this where you have MPI being the middleman to something where OpenMP is doing the job for everything, and you don't need to work on that particular aspect of the distributed part of the code. So your code will become like this. Instead of MPI with all the MPI stuff, the initializations, I send, I receive, wait alls, and you name it. Same thing, much more shorter because it's based on these pragmas that you probably already have, because most of the codes are MPI plus OpenMP. So you will just, you can comment MPI or just eliminate it, up to you. So that was our intent. This is why we're doing this. Simplify the code, still keeping the best of the performance and the characteristics of the code itself. Right, so how we do this, like I said before, there's the whole effort of target offloading. That's for the GPU part, but then actually can be any device these days. Um, any GPU vendor is covered right now by offloading. So then offloading went beyond to remote offloading. The LLVM people and Lawrence Livermore have been pushing this. Johannes Derfert, like I said before, actually his paper got the best paper award in ISC in two years ago. So people in the community understand that this makes sense to a certain extent, this remote offloading thing. So this is one piece that we need to build upon. The next one is, okay, how are we going to do the memory management, which is always the issue, right? Now you have a distributed system, your memory is not coherent anymore. What are you going to do? So we have some previous experience with PGAS model, and we thought, okay, PGAS has two nice things. First, it's quite transparent for the developer. The memory management is happening behind the curtains, but also uses one-sided communication, which is basically by definition better than two-sided communication. You don't MPI creating windows of memory that you have to allocate and this and that, handshaking policies, blah, blah. You don't have that with one-sided. You save all that, right? So we decided to, okay, we're going to have the remote offloading going over a PGAS-supported backend, basically. So that's what we're doing. One-sided communication for the distributed part and OpenMP as it is and at the node level. So implementation, many details here, but basically this is the important one to remember. You have the device, and you have to have this layer of distributed. You can use any, actually, of the conduits that are out there. We tested with GasNet, with XCL, with Nickel. It works pretty well, so you can actually pick what conduit you're trying to use. And then you have the OpenMP runtime, well, our injection in there, and then the traditional OpenMP runtime. So this is how it's implemented. We mostly work under LLVM, but our repo is still private because we're still polishing this. But the intent is to open it. And let's see if we convince the people in the main master trunk to accept this. We'll see. But so far, it's working pretty well. So the API looks it's pretty simple and obvious. You have to do puts, you have to do gets at some point. We hide it behind some a little higher level abstraction layers, but everybody can understand what's going on, that it has some experience with one-sided communication. Like I said, we support major conduit layers and also fabrics. So we tested on different fabrics, all running properly so far. So very quick on that. So let's go into some results, which is what really matters. First thing you'll try is like pure synthetic test latency bandwidth to see if you are matching expectations. So we compare here our distributed OpenMP, put and gets with the MPI put and gets just to see we are at least there. So now we're using the one-sided part of MPI to make it, fair. And latency, so lower better. Different sizes of messages, and as you can see, we are actually beating for most of them the MPI implementation. I don't remember which one was this in particular, and we have a paper. Well, most of these details were already published. The new ones are coming in a journal, and that will cover different MPI implementations if you are curious about that. But the main point of the graph is just to say, okay, this is the delivering performance. This is not going to harm you if you use it. That's for the starters, right? And you might actually beat your actual current implementation using MPI. That's we'll see, right? The other one, so this is in architecture A, which is this one. This is a system we have here in Houston. It's our own little cluster with Grace hoppers. So the host is ARM, and the GPU is an NVIDIA GPU. The other one is the NERSC Perlmutter. Actually, it's basically the same thing, but larger. It's also Grace hopper, if I remember, no, it's A100, but it's still an NVIDIA run system, basically. The main difference is the fabric. We are using our system is InfiniBand. NERSC is using a slingshot from HPE. In both cases, and actually for the slingshot, we are handily beating MPI. We reported this to NERSC SID admins, and they actually reported to HPE, and they think this is a bug in HPE framework. So I don't know what they're doing because this is a lot. But good for us, you know. The code that is under control is performing really well. That I can say. Comparisons a little more difficult to make it apples to apples always, but it's a good thing to be there, right? Bandwidth, the other way around. The higher the better. Message size, the first architecture, the second architecture. So this is our total system. Not surprisingly, MPI does pretty well with the small messages. That's okay, and then they plateau more or less at the same point in terms of bandwidth. And for the applications we care, we are more on this side, right, of the picture. So it's okay. And then for the other one, you see this one here. That's really something happening. Like I said before, we reported because either we are doing something wrong, although we pass all the numerical test, or HPE is doing something really wrong with their MPI implementation. We reported it's been investigated. But the point is that for most of it, we are in the good place with the bandwidth too. So latency and bandwidth. So now we go into applications, right? So this is, oh yeah, no, I need to do collectives first. The other puts and gets, you know. You also need to do some collectives. So we have our reduced traditional thing. Again, this is the total cluster. That's NERSC, and for our cluster with InfiniBand, we are pretty much there with MPI. And for the slingshot, again, there's something going on. So it's starting to be like, okay, there's a case here because this is consistently different. Good for us, not so good for HPE, but I guess they will work on it. Yeah, this is the setup is just for nodes, so we are not really saturating the network at all. For GPUs and 16 nodes for the NERSC system. So that's for the all reduce. The first one that everybody will try, matrix multiplication, Canon algorithm. So the speed up calculation is slightly different than just linear calculation. The matrix is not that big actually, but it's good enough to excite the memory, we're saying. So 16 up to 40 GPUs. This is on NERSC, and we are there with the OpenMP implementation up to the last one. So now we are investigating why we are losing some performance for large number of GPUs. This is with GasNet, if I remember well. So there's an issue also that what of the conduits you're using, stuff like that. But it's competitive. We are close to the point where MPI plus OpenMP is, not mentioning that this implementation of matrix multiplication has been polished for 40 years with MPI plus OpenMP, and we have been working a year and a half on this. So one guy and a little bit on me. So, and then we port wave propagation because the audience, right? Again, this is on our cluster, that's NERSC, pretty much there, pretty much linear in terms of speed up for a wave propagation problem. Could be a little better, but we didn't really want to tune much. So it's like a raw code. There are not much tricks on this, just to see where we are. And we are pretty close to that. We were expecting actually better with our approach for reasons I explained before, like bandwidth and latency. But the issue is that there's always some level of out of control, like is it GasNet, they not the one delivering or something. We are doing deeper profiling to understand why we are not doing a little bit better. We're expecting fully linear, but it's okay. It's a good preliminary result on our cluster. On NERSC, it plateaued really quick. That's expected because it's not really a big problem. So you can imagine, I mean, A100 with 40 giga. When you are here, your domain per GPU is nothing. So it's gonna be mostly communication, right? And that kind of explains why we are doing better with a large number of domains, because our communication, if you remember before, on a slingshot was a lot better than the MPI implementation. So that translates into overall performance where you are mostly doing communication, which is at this level of partitioning of the problem. So overall, we are pretty happy with these results for a year and something of work. The intent is to polish it a little bit more, get to a place where we are happy with all these synthetics. We also have a couple of other applications we are porting because we want to cover different things. We have a flow-oriented one in the pipeline. And then when things are good enough to share, we're going to open the repo to the community, try to convince the LLVM guys to add it to maybe the main track. We don't know. Barbara also mentioned that it might make sense to have a proposal to the architecture board of OpenMP to add this as part official of OpenMP, so then other people can implement it and have different performance results for other architecture that we are not really testing much. So that will be like the next steps. So then it's community and having other people trying it, and that's always important. Other pairs of eyes on it will help, right? So far it's mostly an academic effort, but the preliminary results are pretty good. And let's see, maybe at some point we'll get in some production. I don't know. I've been doing this for 15 years, and how many of these I try and go nowhere? Yeah, but you have to keep trying. Sometime it will work. So I have faith. Questions?
So it's great to see the performance results, but the other thing you mentioned at the beginning is code complexity. So how many less lines of code for your two applications is it with the distributed OpenMP versus
MPI
MPI
it
Next?
Depends a lot on the application, right? Because of them are really complicated communication patterns, then good luck with MPI, Not to mention that debugging that is a hell. And even profiling it as well, John can be testament of what will be if you add some abstraction layers and then you have pointers to hell, basically. This simplifies a lot of that. So I cannot tell you like a rule of thumb how much reduces. The case I showed there, it was like half of the code, this one. So propagator. This is part of the web propagator. That's the hello exchange of the. Yeah. It's gonna be mostly around where you have communication, right? That's what basically we are reducing. You still have to do the parallel part of the computing, which is expressed to the directives that you already have or you will have, right? So it reduces complexity. I said the cumbersome part of MPI basically. I'm not trying to diss MPI as it is. I'm just saying it has introduced complexities and so on. And there's something else which PGAS, I won't say allows, but it simplifies approaches to fault tolerance, which MPI, I mean, it's in the spec now in MPI, but good luck trying. Yes, I tell you that, good luck trying MPI fault tolerance primitives.
Yeah, great work. It reminds me, and I wonder if you were inspired by last year's presentation from a guy from Oak Ridge National Lab who did a similar thing, but their performance was falling a little short in everywhere compared to the OpenMP plus MPI. And, and are you guys talking to them as well? It was a really good talk last year.
Talking about Raja or?
I can't remember who it was. It was just somebody from Oak Ridge, and it was in the auditorium section when they did it last year.
So. Well, because something like this will be either Raya or Coco to a certain extent.
It was a certain application that
But
they
it's-
specific, like you did. They took this one application, they did exactly this.
Okay, I don't remember the presentation. I don't know what framework they were using. Because there are other things out there. I mean, I'm not claiming we invent the wheel or anything here. I'm just saying this is one possibility. There's then for instance, the Japanese like XMMP, which is something like this, also with PGAS. We know them. We exchange some ideas. Not exactly the same thing, and they are not in the OpenMP spec. That's a problem because then compiler implementations get complicated. So, yeah. But okay, thank you for the feedback.
Any last questions? All right, we got one more here.
My question is about this missing scalability for this application. I mean, you should really achieve linear scalability for this wave equation propagation.
Yeah,
and my point is, I mean, how can you achieve overlap of computation and communication in this framework? Maybe that could be an explanation.
Yeah, no, we have all the RMA-based asynchronous for the starters, so there's no an issue with that. Now, the other question is how we get the perfect scaling for more. That's always a problem, right? Because as soon as you start going in a large number of domains, you have the communication computing problem anyway happening. And even if you use little or very smart communication, you are paying an overhead, right? With PGAS, we believe smaller than MPI, but still there's some. And yeah, we are looking at those. That's a good fair point.
All right, thank you, Mauricio.
Okay, thank you.